Okay, so to make the potential twice as large, to make it 4 times as large, we go from 1 volt to 4 volts. And we're starting at a distance of 2 meters. Where do we end up? C, half a meter. Yeah, and most of you got that. Excellent. Now, if we take that sheet representation of the electric potential for positive and negative charges and put it together, this is what we get. We get a surface that sticks up near the positive charge and sticks down toward negative infinity near the negative charge. And what I'd like you to try to do is imagine how this is basically the same as the picture we had before of an electric dipole. Remember, for an electric dipole, the field lines are going from the positive charge to the negative charge. But how do we relate what we see here to what we see here? Well, first of all, whenever you see electric field lines, you should imagine, okay, what happens if I put a test charge at some point? Well, what about out here? Well, the electric field is mostly pointing in toward the negative charge there. You would find a force pulling it toward the negative charge. And halfway in between here, the field lines are very concentrated. That means the electric field is strong at that point. I think you can actually see that a little bit better here. If you try to imagine putting a charge here, it would fall away from the positive charge, right? Or if it's halfway in between the positive and negative, that's where the surface is the steepest. The steepness of the surface here represents the strength of the electric field. In some ways, this is a more intuitive way to represent a dipole field. It's a little bit cumbersome, though. So that's how you should think, anyway, about the relationship between electric potential and how it depends on space and the electric field. But you know, if you're really doing it right, you'll have this picture in your head of 3-dimensional field lines emanating from the positive charge and going to the negative charge and curling around like that. Okay, so when we have a positive charge sort of attached to a negative charge some way or other, and it could be in a molecule or any number of other ways, then we have what we call an electric dipole, and we're going to treat this thing as a unit. And we'd like to know what happens when we stick it into a uniform electric field. Clearly, there's an electric force on the positive charge, which is going to the right, and a force on the negative charge going to the left. That's tending to straighten out the dipole, to align it with the electric field. Now, a great deal of chemistry, and including biochemistry, can be explained by the dipole forces between molecules. So I think it's a kind of an important thing to understand if you're going to understand biochemistry at this level. So we'd like to do the energetics of this. Let's think about it and do the math. We've got an electric field, and we have this dipole set up. So we have the charge plus Q on this end, minus Q on that end. They're a distance d apart. Now, we will say that the angle from the positive charge to this horizontal direction, the direction of the electric field, is theta. And we want to ask what happens, how does the electric potential energy change when the dipole goes initially from being transverse to the electric field direction to an angle theta. So in other words, we're going from theta equals pi over 2 to some value theta. Well, that means the positive charge has moved a certain distance along the electric field direction, which we can calculate. And we see that since this is d over 2, the hypotenuse here, this is a right triangle, then this is d over 2 times cosine theta. So now we know how far along the field the positive charge has moved. And so we can calculate, and the negative charge goes the opposite direction. So the change in potential energy is downward. It's minus 2 times Q times E is the force, times the distance is d over 2 cos theta. 2's cancel, so you just get Q d E cosine theta. And we define something called the magnetic or the electric dipole moment as P equals Q times D. So in the final line here, we just say it's minus P times E times cosine theta. We don't always necessarily have a nice positive and a negative charge. It could be more complicated. So the field is tending to align the dipole with the electric field because it's energetically favorable to do so, right? The state where it's anti-aligned is higher potential energy than when it is aligned with the dipole, with the electric field. Now, the way that electric dipoles arise on the molecular level is due to charge separation. You know that in a water molecule, oxygen and two hydrogens, that the oxygen, the available energy level states for electrons in the oxygen tend to pull the electrons toward the oxygen and away from the hydrogen, leaving the hydrogen proton almost bare. That gives a net electric dipole moment in this direction for a water molecule. And the value of it in these units is 6.2 times 10 to the minus 30th coulomb meters. The dipole moment P is equal to Q times D. It's just like you had a little positive charge and a negative charge stuck together. And in fact, these dipoles can interact with each other, and that's how water molecules bond together. When they're in the liquid state, the hydrogen from one is attracted to the negative oxygen of another one, and they form these chains and groupings, and when water becomes crystallized, then you get these beautiful hexagonal patterns due to the dipole bonding forming crystal structures. And that's why snowflakes look the way they do.